Welcome back, grade 9 science students. Today we are going to discuss our first lesson in fourth quarter. We are going to talk about UAM or Uniform Accelerated Motion. And then our important words and their meaning, we have projectile motion, UAM. So when we talk about UAM or Uniform Accelerated Motion, it has two components, horizontal and vertical dimensions. When we say horizontal, these are the movement of every objects from here up to here, no? Horizontally, or it could be also in this direction. And when we talk about vertical, these are the falling objects or objects that are moving upward. And then we have also other examples of horizontal dimensions and vertical dimensions of UAM. We have here a girl riding the bicycle, and then this man is jumping from the building, right? Next, we have also another example. This one is horizontal dimension and vertical dimension. And of course, aside from identifying the two dimensions of UAM, in this video, we are also to solve different problems that deals with uniform accelerated motion. That being said, we have different situational problems to solve in this video. So when we talk about problems, just like this one, damaged motorcycle, the first thing to do is to find different tools, no? To find this toolbox to repair this damaged motorcycle. So we need this toolbox. And of course, we have also problems about UAM, horizontal and vertical. So our toolbox in solving for UAM problems are this one. We have the formulae, no? The uniform accelerated motion formulae. We have different or four formulas to solve the different problems that involves UAM. All you have to do is to remember these four formula, okay? We have the BF, that stands for final velocity. BI, we have BI, initial velocity. We have also acceleration, then the time. So since we are dealing with uniform acceleration in this video, I would like to show you these numbers here that tells us the difference between uniform acceleration and non-uniform acceleration. We have here 5 lines, and then the first line is an example of uniform acceleration. Why? Because if we determine the change of velocity, because these are examples of velocity, no? 5 meters per second, 10 meters per second, 15 meters per second, 20 meters per second, 25 meters per second, and so on. Now, if we take a look at the difference between the increasing velocity, when we say increasing, I am saying it is increasing because it becomes bigger and bigger, and because it is acceleration, because when we say acceleration, the velocity or the speed should becomes higher or increasing or becomes bigger. In this case, this is an acceleration because it becomes faster, no? It becomes bigger or it is increasing. So we have here 5, then it becomes 10. So the increase is 5. Here from 10 to 15, still 5. From 15 to 20, still 5. From 22 to 25, still 5. From 25 to 30, still 5. Meaning 5, 5, 5, 5, 5. So it has uniform acceleration. Meaning to say, it has a uniform of 5 meters per second increase of velocity. No? It increases up to 5 meters per second. So this means that it is line number 1. This one, line number 1 is example of uniform acceleration. What about number 2? 5, 10, 20, 25. Of course, 5 to 10, so 5. Then how about 10 to 20? Is it still 5? No, it is 10 meters per second. Meaning to say, it is not uniform acceleration because from here up to here 5, then from here to here 5, and then from 10 to 20 it becomes 10, then it goes back to 5, and then 25 to 35, 10 again, then 35 to 36, 1, 36, 39, 3. So it is not an example of uniform acceleration because the change of velocity is not the same or is not uniform. How about line number 3? Line number 3 is still example of uniform acceleration because it increases by 2. How about line number 4? Not uniform acceleration because 2, 4, 6, 8, then 14. So not acceleration. How about line number 5? Line number 5 is not accelerating. it is not an example of uniform acceleration. It is also not an example of non-uniform acceleration, because line number 5 shows us that it is not accelerating. The velocity remains 5 meters per second, no? Remains the same all throughout, constant velocity of 5 meters per second. So meaning to say, this is not accelerating. So again, in this pile of numbers, line number 1 and line number 3 are example of uniform acceleration. Okay, let's proceed. The first lesson about UAM that we are going to study is about horizontal dimensions. Okay, these are the moving objects that moves horizontally, just like an airplane that is preparing for takeoff, no? It moves horizontally. So here, an airplane from rest prepares to take off, then it travels 5 meters per second in 1 second, after 1 second, and then it travels 10 meters per second in 2 seconds. So it is increasing, and therefore it becomes faster and faster. And then in 3 seconds, it travels 15 meters per second. This is an example of uniform acceleration because the change of velocity remains the same, 5 meters per second. Also here, 5 meters per second. And to have more understanding about this concept, why not hit the pause button and read the descriptions? Okay. So now, let's dive right in. The first problem of horizontal dimensions of uniform acceleration. An airplane from rest accelerates on a runway at 5.50 meters per second for 20.25 seconds until it finally takes off the ground. What is the distance covered by the takeoff? So, for example, this is our airplane. Again, if this is our airplane here, it travels on a runway and accelerates at 5.50 meters per second squared for 20.25 seconds until it finally takes off, no? Until it finally takes off. Okay, and the question is, what is the distance covered? So how far is this, no, distance here? How far is the airplane from here up to here until it finally takes off? Okay, this is the distance we are going to solve here. Again, as what I have said, this is now a problem, and therefore we need our toolbox, no, or the formula that we are going to use to solve this problem. So just remember, we have here our acceleration is 5.50 meters per second squared, and the time is 20.25 seconds. These are our given numbers, and of course, because it talks about from rest, meaning to say the BI is equal to 0 meter per second because it starts from rest. So let's go to our formula. We have here our given numbers, and then the formula 1, 2, 3, 4. Now, the first thing to do is to identify what formula should we use to solve the problem. So in that case, just find out what formula that contains most of our given numbers. Here, number 1, for acceleration, number 1 has A, so correct. How about number 2 has A? Correct. How about number 3? It has A? No. So, wrong. How about number 4? It has A? Yes, this one. So, check. Okay. We still have 3 remaining formula. Now, how about the T here? Is number 1 has T? Yes, correct. How about formula number 2? Yes, it is also letter T, or the time. How about formula number 4? No, it doesn't have T, so it is wrong already. So we have only 2 remaining formulas. How about BI? This one, BI. Is number 1 has BI? Yes. Okay, correct. How about number 2? It has BI, still have BI. And then, what about the factor that we are going to find out? The D, or the distance covered, D. Is formula number 1 has D? Of course. No, nothing in number 1. So finally, because number 2 has D, meaning to say, check, and therefore the formula that we are going to use is formula number 2. As easy as that. And then, since this is our formula, I have here preparing the ready-made solution that you're going to base your solution. So again, since we have the formula, all you have to do is to plug in the different values in the formula. So we have here 0 for BI, 20.25 seconds for the time, and then 5.50 meters per second squared for A, this one A, and 20.25 seconds for the time, then the square. Okay, next thing to do is to solve the equation. Now, 0 because it is 0 times 20, so the answer is 0. Then 5.50 meter per second squared times 410. Where did this 410 came from? It came from this 20.25 seconds times 20.25 seconds because it has square root of 2. So the answer is 410.0625 second squared, and then divided by 2. Then it is multiplied by here. So no, you multiply the 2 here and then divided by 2. The answer is 1,128 meters. So again, 5.50 meter per second squared times 410.0625 divided by 2. The answer is 1,128 meters. So let's go back to our problem. Our airplane, this one, accelerates on a runway, until it finally takes off. So the distance from here up to this one, after it finally takes off, is 1,128 meters. As easy as that. So again, to have more understanding, I have here sample problem number 2. It says a motorcycle from rest. So when you say from rest, VI is equal to 0. Okay. Accelerates uniformly over a time of 3.25 seconds and covers a distance of 15 meters. What is the acceleration of the motorcycle? So it says a motorcycle accelerates at a time of 3.25 seconds and covers a distance from here up to here of 15 meters. The question would be, what is the acceleration, or the A? What is the acceleration? So when you look for the formula, the shortcut that I'm preparing here is this one. This is now the formula, because as we check it to our toolbox, this one, you will find out that still number 2 is the usable formula, because it contains the VI, it contains the T, this one, and it contains the D, and it also has A. Therefore, number 2 is still used in our sample problem number 2. And this is our solution. The same formula, D is equal to VAT plus AT squared over 2. I would like to remind you that our formula for number 2 contains this one, over 2. Okay, I forgot to write the divisor 2. So in this case, we have here the D 15 meters, the VI 0 meters per second, the T 3.25 seconds plus A times 3.25 second squared over 2. Okay, so 0 plus 3.25 seconds times 3.25 seconds. The answer is 10.2625 seconds squared divided by 2. So the solution is this, 15 meters per second, 15 meters, A equals A, because it is divided by 2, 10 divided by 2, the answer is 5.28 seconds squared. Now, so divide both sides by 5.28. So this one, divided by 5.28, also here 5.28. So this one, 15 divided by 5.8, the answer is 2.8 meter per second squared. This is our acceleration. Right? I will be glad to receive some questions to those who are viewing this lesson video. Just write your questions in your comments below. Do not hesitate to write your questions, okay? Let's proceed to our next dimension of UAM. We have here the vertical dimension. This one, example is the jumping mountain climber. No? It jumps on a hill, or it's jumping from the top of the mountain. So this is an example of vertical dimension because it is moving in downward direction. So it is also known as this one, if you are familiar with this terminology, the free fall. Yes, this is an example of free fall. It is only acted by the gravity, which is constant, 9.8 meter per second squared. No, meaning to say, all moving objects downward, when all objects that is falling downward has a uniform acceleration of 9.8 meter per second squared. Just like our example a while ago, that when we say 5, then it becomes 10, and then it becomes 15. So the constant acceleration is 5 meters per second. The change in velocity 5 meters per second. Here, all moving objects downward has also the same, no? Constant acceleration, not 5, but 9.8 meter per second. Okay? So now, let's proceed to another slide. This one, the one that I'm talking here. From the hand of this boy, it has, because it is still from rest, because it is still on his hands, and therefore it has an acceleration of 0, no? No acceleration because the stone is still on the hands of the boy. Now, when the boy starts to let go of the stone, it will eventually fall down. Okay? And of course, at an acceleration of 9.8 meter per second squared, constant. So 9.8 plus 9.8, 19.6, 19.6 plus 9.8, 29.4 plus 9.8, 39.2. The negative sign here indicates downward direction, indicates direction, because if you remember, if this is our Cartesian plane, no? If this is our Cartesian plane, this is the x and the y. This is the positive y and the negative y. So because it is moving downward, it indicates negative direction. No? Okay. That is why it is negative 9.8 meter per second squared, all from vertical dimension. So now, let's proceed to our sample problem number 1 of vertical dimension. Ben is playing with his ball on top of a building. So this is our building, then he's playing the ball right here. But the ball fell and hits the ground after 2.6 seconds. So eventually the ball falls down. Then it reached the ground at 2.6 seconds. Then what is the final velocity of the ball just before it hits the ground? So just before the ball touched the ground, if this is the ground and then this is the ball, so just before the ball hits the ground, no? What is the final velocity? What is the velocity? What's the speed, no? How strong will the ball hit the ground? So in this case, in our formula, we will change d to h because it will indicate now height. For horizontal, it talks about d, displacement. But for vertical, we change d to h to indicate height, okay? Position of an object from top to bottom. So again, please remember the given numbers. We have here 2.6 seconds. And of course, the VI is 0 because from rest, no? While the ball is on, while Ben is still holding the ball, it is from rest, and therefore the initial velocity is 0. So right here, when you analyze the problem, because the ball fell down, therefore it has a constant acceleration of negative 9.8 meter per second. This one right here, and the t is 2.6 seconds, and the VI is 0 meter per second because while the ball is still on his hands, it is from rest, and therefore 0 meters per second. So we are looking for the final velocity and the height of the building. So the formula that we're going to use is what? So to make the video short, when we look for BF, automatically the formula that we need to use is number 1 because it has the unknown variable VF, and then we have the A, acceleration, we have the T, 2.6, and we have the VI, 0. So complete VI. The BF that is unknown can be solved using this formula number 1. What about the H or the D, the height of the building? Again, to make the video short, the formula that we are going to use is this, no? D is equal to BIT plus 80 squared, or 1/2 80 squared divided by 2. So let's try to solve the problem. We have here BF is equal to BI plus AT. So BF is equal to BI 0 meter per second plus acceleration negative 9.8 because the ball is moving downward, so negative 9.8 meter per second squared times time, which is 2.6 meter, 2.6 seconds square, no square, okay? So BF is equal to 0, so cancel. 9.8 times 2.6, how much is the answer? So to make the video short, negative 9.8 times 2.6, the answer would be, let's proceed to our encoded solution. This one. Just multiply the two, the answer would be VF is equal to negative 25 meters per second. So we have here the value for the final velocity. So if this is the ground, this is the ball must have the velocity or the speed of negative 25 meters per second before it hits the ground. Okay. Now, this one. What about the H or the height of the building? no? The height of the building. When the ball falls towards the ground, how high is the building? How high is this building, no? So h is equal to bit plus at squared divided by 2. So doing the solution, this one and this one, we come up with the answer height 33 meters. So the height of the height of this building is 33 meters. Just solve the problem properly, okay? Where did we get this 0? It's because it is 0 meter times 2.6. 0 times 2.6, the answer is 0, of course. Then we have here 2.6 times 2.6 because it is squared. So 2.6 times 2.6, the answer is 6.76 second squared. And then you multiply 6.76 by negative 9.8. The answer is negative 66.248 meters. Of course, divided by 2, the answer will be 33 meters. That's it for solving the UAM vertical dimensions. Of course, thank you so much for watching. If you like this video, please subscribe, please support, and please share to your classmates and to all your friends, okay? Thank you so much and have a nice day. See you in our next lesson about motion in 2 dimensions or projectile motion. Goodbye.